history of glasses, but not so much about the history of glass itself, but more how we discover new glasses. Like, so we heard this morning about all those glasses and how amazing they are and all the amazing technology that were enabled by glass, but how did we come up to discover those glasses, and how can we make sure we continue discovering new glasses, but maybe hopefully we don't have to wait centuries, we can discover this like much faster than before. And so, yeah, I mean, we went through this already this morning, but so you have all those glasses that have unique properties, like maybe the crystallo glasses, like the Venetian glass that was the first glass to be consistently transparent. Then you have the glasses like Pyrex that is very low coefficient of thermal expansion, and glass fibers that can conduct lights and photons over like miles. And so, how did we come up to discover those glasses, and how do we make sure we discover new glasses? So, discovering glasses, to some extent, it's really about discovering chemical compositions, and that's one of the beauty of glasses, that you can pretty much put the entire periodic table inside glasses, but it's how do we figure out like which element to put and which proportion? Like that's really the challenge. And so, for example, if you think about the crystallo glass, like this Venetian glass, like it's really the addition of the manganese oxide that initially enabled this ability to make transparent glasses that you can actually go through. Then when you think about the flint glass, this ability to make glasses that have a higher refractive index, that was through the addition of lead oxide. And then if you think about the window glass, so it's like the base ingredients of a window glass, they were here from the very beginning, like since the Egyptian glass, like some sodium oxide, some calcium oxide, some silica. But how did we come up to this, finding this exact magic formula here, like this 116, where you have 1 mole of sodium oxide, 1 mole of calcium oxide, and 6 mole of silica? Like there is limitless ways of how to mix those different oxides, and it takes a lot of time to come up with those exact formulation. Same thing with the Pyrex glass, like it's how do we figure out that adding boron oxide is going to decrease the thermal expansion of glasses, glass fibers, how do we make a pure glass, how do we come up with optimal formulation for those bioglass that we just heard for medical application. So this process becomes harder and harder because to some extent maybe we have found the obvious glass at this point. So if we want to make new discoveries in the future, we need to go beyond and find new glass composition and new optimal way to mix those different atoms together. And this is a very complex process because there's just like so many possibilities. Like first you have the entire periodic table that you can access to. And then, once you have those atoms, you can mix them with any fraction you want. That's another beauty of glass, that it doesn't have any stoichiometry requirement like crystal. You can have any fractions of all of those elements that you put together, and many of those can form a glass if you quench them fast enough. So, I mean, there is this number here that Professor Zanotto came up with that if you just consider like how many glasses can you form with the periodic table, and just considering like 1 mole increments in the way you mix those elements, then you can have about like 10 to the power 52 possible glass compositions, which is an astronomical number. It's even hard to understand what it even means, but like it's maybe one thing is to compare with how many glasses we have actually made so far. And so at this point, if you look at the existing database, there is about like 400,000 glass. Those are all the glass compositions that have been tested since like the Egyptian glass pretty much. And so this is really a tiny fraction of all the possible glasses that can be made. And so that's a big opportunity for glass, because it means that there is like so many exciting new possibilities, and we have really scratched the surface to some extent. But that's also a curse, because like when you have so many degrees of freedom, so much possibilities, like where do we go? Like where do we start? In which direction? Which oxide? Which fractions? Like it's a pretty hopeless task to some extent. And so the question is, like, how do we discover those new optimal glass compositions? Like if we want to come up with a new product in the future, like maybe this like this new types of glass that's going to enable quantum communication. Like, so we need to come up with new glasses that have unique functionalities, unique properties, and how do we find what's the glass composition among those 10 to the power 52 that's going to achieve those optimal properties. And so if we come back to the history of glasses, historically the way it has been done is really empirically, and that to some extent that's the first paradigm of material science. It was really based on just empirical experience, intuition, sometimes a little bit luck as well. And so like this is really what initially has enabled many of discoveries in glasses. It's a lot of serendipity, like sometimes a failed experiment that can turn out into something like amazing, like the glass ceramics, for example, or trial and error, like a persistence, and just trying, like this Edison discovery of the light bulb. Like it just takes sometimes like thousands of iterations until you can find the right design that's going to give you the property that you want. And obviously this can work to a certain extent, but when you have like the entire periodic table available to you, you cannot just try every combination. It would just take like several lifetimes or probably more than that. So it's just a very daunting task. So like one way that I like to represent this is like, so you have a given space, that's a compositional space. That's the space of all the composition that you have access to. Here I'm representing that as a 2D space, but in reality, every time, I mean, you have like hundreds of dimensions, which are all the elements that you can mix. And somewhere in this space, you have like one glass. That's the optimal glass. That's the one you want to find. And it's just a very tiny position within a very, very large universe of possible glass composition. And the question is, how do we get there? And so obviously the first option is this Edisonian approach. Like if you're very persistent, or maybe a lot of very brave students in your group, like you can just try until you find something that is close enough to the optimal glass. And this thing has worked in the past, but it's just like it's not a way that is really in line with the the 21st century and like this need to accelerate the discovery of glasses. So then there's this second paradigm. Is like okay, maybe we can understand enough about the physics or the chemistry of glasses to use science to directly pinpoint what's going to be the best glass composition. And there is a lot of things that you can do with that, but there's also so many questions of things that we don't understand about glass, about the glass's state itself, and about how the chemical composition of a glass influences properties, that there is some limit of what you can do with that. Our level of understanding of glass is not ready yet to really support completely from scratch the discovery of new glasses. And then, so there is the third paradigm, which is computational science and the ability to simulate glasses. And so that's really something that over the past decades has changed many things in material science and also in glass science. The ability to directly simulate glasses at the atomic scale by simulating the motion of the atoms and how they connect with each other. And based on that, what this thing has really enabled is to do some high throughput exploration, to just simulate potentially millions of glasses and screening them on the computer so that you can really focus only on the most promising glasses in the lab rather than having to generate like thousands of glasses like Edison did. And so this can really change many things, but there's still some challenge there. First, if you want to screen glasses using simulation, we need to make sure that those simulations are actually giving you something realistic, which is not always the case. But also, even with that, we are still limited to maybe simulating like millions of glasses. But so we are still very far from the 10 to the power 52 glasses that we want to explore. And so, like, what this thing is really enabling you to do is exploring faster spaces. And so like one way to represent that is that we can just explore the space in a high throughput fashion, which is kind of like pure brute force. It's just you try every single composition until you find the right one. And again, this can work to some extent if you're patient enough, but it's just a process. It's very slow. Even with modern computers, we're still not able to simulate like the 10 to the power 52 glasses that we need to really completely explore all the commercial space that we have access to. And so like the question at this point is, so this is what we have been doing so far, and it's been working great, but if we really want to accelerate, like if we don't want to wait like another century before the next glass, like how can we accelerate that? Like how can we, by several orders of magnitude, accelerate the pace at which we discover new glasses? And so this is where really artificial intelligence and machine learning is one option to solve this problem. So the idea is, so far, we have those three paradigms. And so we have everything that is based on intuition. That's maybe the first paradigm. Then we have like the knowledge, the ability to learn. That's the second paradigm. And then we have the computers that can do things like human, but just much faster. And so like, I think the idea of artificial intelligence is that you can really combine those things together. You can combine the ability of humans to learn, but also you can also benefit from the speed of computers. And that's, I think, the big, the core idea of like the fourth paradigm, which is like relying on big data, artificial intelligence. And the idea of this is to at the same time benefit from computers' ability to do things very fast, much faster than us, but also to have this ability to learn and not just do a pre-existing recipe, like to have the ability to adapt to data, learn from data, and make some decision based on that in the very same way that humans would do. And so the idea of this is really to replace the process of a human trying to discover a new class, to replace that by basically a computer. And for example, deep learning or machine learning is one of the techniques in artificial intelligence that can achieve that. And so the idea of machine learning is really to start with data. And the good news is that we have a lot of data. Like we are generating a lot of data. Sometimes this data can be well organized in database. Sometimes it's data available in papers or in patents. But there is a lot of data, and the rate at which we produce data that keeps accelerating exponentially. So we have this huge amount of data. And computers are very good to analyze data, find patterns in data, find some relationship between data that might not be obvious to human, but to computers becomes easy to spot. And so this is where machine learning comes from. And so if we wanted to define what machine learning is, so my definition would be the following. So machine learning is the science of getting a computer to learn how to perform a given task, for example, finding a new class, but to learn by example without being explicitly programmed on how to perform this task. So in many ways, it's learning like humans. Like many things we learn in life is just by observing rather than learning the theoretical idea behind what we do. Like the way we learn how to walk is not by solving the laws of dynamics. We just learn by example and trial and error to some extent. And that's pretty much the same idea for machine learning. And that's really changing the way we use computers. Because before machine learning, if you wanted to use a computer, you have to provide an algorithm to the computer. You have to provide a recipe. So for example, if you wanted to teach a computer to make a cake, and I'm sorry I know lunch is coming, so I don't want to make you more hungry, but I think the cake analogy has some merits. So if you wanted to teach a computer to make a cake, then you would need to provide the explicit recipe to the computer. You would need to say, put like 1 cup of flour, 1 teaspoon of sugar, 1 egg, etc. And we need to say, do this, do that, etc. So that we need to provide the recipe. And to some extent, that's how humans have discovered classes so far, by following some recipes and then changing this recipe by intuition. So here it's very different. In machine learning, you don't provide any recipe, you just provide data. So you would provide a lot of data of cake number 1, cake number 2, cake number 3, and the list of ingredients. And then the computers will learn from that, find some patterns, and then based on that, you can ask then your computer to tell me, I want to do this new cake that I've never done before, and then the computer will actually tell you the recipe. So it's completely reversed paradigm as compared as before. Before we provided the recipe to computers, and the computers give us an answer. Now we provide data, and the computer gives us a recipe in return. And the hope is that the computer, in that sense, can tell us how to make new glasses simply based on data. So that's the promise of machine learning. And so again, if we come back to this picture here, the idea is that we start with some data. Those are the data that we have available so far. That can be like database, SciGlass, AlGlass, or any data that has been published in a glass journal. And then from this data, we feed that to computers, and we ask the computer find some patterns, try to learn something from those data. And then the computer will come with the recipe. How do I discover this new glass that doesn't exist yet? So the computer will maybe make an attempt. Most likely it won't get it right the first time, but that's the good thing about machine learning, is that the more you generate new data, since machine learning only relies on data, the more you have new data, the more it learns, and it becomes more and more accurate every time. And so this is the idea of what machine learning can do. It's really to help you pinpoint your search towards a specific direction and explore this space much more efficiently than before, and guide you towards the most promising glass much more efficiently. So this is where really we can save time. Avoid exploring like space of composition that are not promising, and really focus towards the most promising one based on whatever patterns in the data sets computers are able to find. So I just want to show you some result about what it looks like, but pretty much I just have two slides left. So this is some example here of compositional maps, where you have free oxides, and so you have many ways you can combine those free oxides. But what the machine learning algorithm can tell you is directly tell you for any combination of those free oxides, it can telling you like what will be the density of the glass, or what will be the modulus, which are important properties for glasses. So the idea is that you can really explore large compositional space much larger than before. And the other thing is that if you start, on the other hand, with what are the specs you want for your glass, what are the properties that you want, like the machine learning algorithm can directly pinpoint towards a promising families of glasses. Like just think about if you wanted to invent a new Pyrex glass, for example, and you didn't know that adding B2O3 is the right solution. All you need to know is, I want a low coefficient of thermal expansion. How do I find out that B2O3 is the right oxides to add? And so that's really the idea of this types of approach here, which we call it like the glass selection charts. The idea is that you start with the property that you want, like a certain level of stiffness, a certain level of density, or maybe a certain value for your glass transition temperature. And based on this ability of machine learning to just explore large compositional space very quickly, then you can directly pinpoint what is the family of glasses, what are the types of oxides that you should be using. So it can really allow you to narrow down your search to a much more targeted domain without having to just try every single oxide that you have in your lab. And so we think that this is really going to change the discovery of glasses. I mean, to some extent, it's already used by companies. At least certain companies have already embraced those techniques. And so we think that it can really accelerate the way we discover glasses, so that we can support new technology with new types of glasses with exactly the right combination of all those properties. And so there's still some challenge for that, of course. There's still some work needed. The first thing is that everything relies on data, and data is not always accessible, so we do need more data, more accessible data, so that's one thing. There is also some challenge about machine learning and AI in general, because AI was not developed for materials. It was developed for much different purposes. And so it's not really suited to handle the challenge with materials. Like we have data, but we also have uncertainties. We have data, but usually we don't have that much data, or at least much less data than a company like Google. But on the other hand, we have some knowledge that usually tech companies don't have. So there's a lot of challenges about how we combine seamlessly knowledge and data within the same algorithm. So those are all things that I think are pretty exciting to explore. But I think there's a lot of promise in those types of approaches that are leveraging data, but also hopefully leveraging the human intelligence and the knowledge of the chemistry of and the physics of classes that we have accumulated so far. So yeah, that's well, you will never see the last slide, but I guess that was just yeah. Oh, okay. A list of. I wanted to show my students since they are the one that are doing most of the work. And thank you so much for it.